Okay. So let's discuss the problem in number 5. In practice set, it's like 3 or I think a 4. I exactly don't remember, but uh, your TAs have notified me that you have some doubt regarding this. So can somebody summarize the doubt? So she has also notified me what is the possible doubt, but the thing is, maybe she also got somewhere wrong uh, in getting your doubt. So let me ask you, what was your doubt? It's like uh, means you are supposed to find parametric equations for the line tangent to the curve of the intersection of these two surfaces. Yeah, I think screen is visible to all of you, right? Yes.
Yes, sir.
Yeah. So can someone summarize it? Say you have doubts, so you uh, can tell better. Okay.
Sir, it will be plane or line? Tangent plane or
See, whenever two surfaces are intersecting, okay, means you take any, you can say ball, okay, and you take a rectangular plate, okay, or means like a knife, you can say it's a rectangular knife, and then you just cut down that in between somewhere. Okay. So means you are following some trajectory. So that may be a that rectangular plate. You can have that equation. So when it's intersecting, what you are obtaining means you are obtaining either a kind of when you are either a circle, or you are obtaining a somewhat like elliptic body. I mean elliptic ellipse, you can say. So is that what is the circle? Means you are only interested in the boundary of the circle. Circle means you are only interested in the boundary. Boundary means it's a curve. So curve means you are that's curve. So at any point of the curve, what you can expect? You can expect a line. As simple as possible, I can explain. Now you can instead of ball, you can take a cylinder. Okay, you can take a cylinder and you can cut it down, okay, by a plane, okay. So what you will obtain means it depends on the cylindrical shape, but you are obtaining a curve where it is intersecting. Am I correct?
yes, sir.
So at any point of the curve, you can talk about the tangent line. Okay. If you are obtaining a surface, okay, if you are obtaining a surface, then at any point of the surface, you can talk about the tangent plane. Okay, if you are obtaining a surface, but you're not going to obtain a surface when you're intersecting two surfaces. Okay, so it's very clear that it's and in the statement also. Okay, in the statement of the problem, it is asking you to find parametric equation for that line tangent to the curve. Okay, the curve of intersection of the surfaces. So your interest is where it cuts, and that curve uh, at that means at any point of the curve, what will be the equation of tangent line? Okay. Now here is also given at point P naught 113. You have to find it. Okay. So it's and I hope the mathematical thing is very much clear. I hope so. Okay, do you have any doubt about it? It's like, see, if you denote the surface by, let's say, F, I denote the surface by F, and let's denote this surface by G. G equals to this minus 11 equals to 0, I can write it. Now, they will intersect somewhere. Okay, they will intersect somewhere. So when you are going to obtain a curve, okay, somewhere means you are going to obtain a curve. Okay, maybe a closed curve, maybe a not non-closed curve, maybe it depends. Okay. Okay, so let's see. Okay, so it will obtain. So, but now see that one thing is there. I'm just trying to explaining that how that mathematical thing is taking into account here is like this intersection, that curve of intersection will be a part of the surface F as well as the part of G. Okay, and you are trying to identify a tangent at any point. Okay, please bear with my time. Okay. Okay, tangent line. Now, at any point of this, so tangent line, is going to be, we have shown already, we have our observations that it is orthogonal to the normal to the surface. So if you consider this is a part of the surface F, then it is also orthogonal to the that normal grade F. If you are also, because this is also a part of the G surface, so this also orthogonal to the surface grade, means that orthogonal to the normal, that's grade C. Okay, now see this. So at any point, so this tangent line is orthogonal to grade F. This is also orthogonal to grade G. So if a vector is orthogonal to both, so it lies in the direction of A cross P. You know that, right? Grade F cross grade G will give you the vector which is orthogonal to both. It's also orthogonal to grade F and also orthogonal to grade C. So the directions, okay, will lie in the direction of grade F cross grade this vector. Now you have that equation now, x minus x naught divided by, okay, is equals to y minus y naught divided by z minus z naught divided by. So this grade F cross grade Z is this Ix component, I coefficient, J coefficient, K coefficient, and at point P naught you have to evaluate. Okay, so I'm here. I hope this is so let's say grade F cross grade C is a vector. Let's say this is somewhere H. Okay, this vector H. So Hx, I'm just writing here now. Okay. So separation H means X component at P naught, similar is equals to Hy component at P and Hz component at P naught and equals to T. Taken that. So this T is a arc length parameter. Instead of that, you can also take S or any other notation you are favorable with. Okay. Any doubts so far now? Okay, fine.
Sir,
Let's move ahead. Yes.
can we do like substitute z square from one equation into another equation?
Yeah, you could do that, but how does it help you? See, as we have seen in Lagrange method, okay, we have seen somewhere that substitution may not go smooth in every time, may not go smooth every time. Means what you are expecting, you may or may not be able to get there. Okay, so I have also a doubt here. So that's why I try to escape from this. Okay, so here let's see y z square. You can also take y square equals to y also is a dependent variable, and x and z are also independent variables. Okay, similarly, I can also treat this x as a dependent and y and z are independent variables. Okay, so question is now again which way you go, is whether it will always work.
So means
Okay,
I'm asking that if we substitute means from second 2 into 1, then we will get the equation of intersecting curve, no?
yeah, yes, it should be. It should be. Means
And
when you are
then
substituting, means when you are finding the point of, but the thing is, yeah, you will get a equation in x and y. So you can write y as a f of x. So you will get a, if you are, if it is possible to get y and f x, you will get a actual equation, it's exact equation of curve.
and then we can find grade f and then do dot product with the point to get the tangent equation. That's correct?
You can try that, and you can try that and match with the answer. We'll see that. Okay. I
Okay.
okay. So because sometime uh, what is my point is, see, when you are having the equation, okay, when you are having these, if you are substituting z square equals to this, okay, you are getting is equation which is involving only x and y, and when you are working with the grade f, okay, it has only x component and y component.
Yes, sir.
Okay. On the other hand, if you're talking about here, you're having all the components. Okay,
Yes,
x,
sir.
y, and z.
That
Okay,
only was doubt.
so I think this is very clear that I think from here what I can say that it's why to take risk. You can say, okay, because I'm still not able to convince myself that you can replace z square equals to the same. Okay, I will look into it again, and let's see whether I do have any example where the substitution method will may not go smooth as like in Lagrange. I will also look into it. Okay,
Okay, sir.
yeah. So I think, but that point is very clear when you are talking about z square equals to something and you are replacing here, that grade f only give you the component in the direction of I and j, not in the direction of k. Okay, but
Yes.
okay, right. So okay, so now we are going to start with the multiple integrals. Okay, so some line integral or double single means like single integral. You have already seen like integration f of x dx. Okay, this is one of the application of that, which I hope we have already seen it maybe in the previous course session as well. Okay, but let's okay. So we will look into it again. It's not a problem. So it will use the this, like it will give you a flavor that means how this volume formula has come. Okay. Okay. So to understand this, I think it's if you want to find a volume of a solid of a revolution. Okay, so it's only here it's you require an axis of rotation. Okay, means you have a some wall, you have tied a rod here. Okay, and you tie means here is a rod, so this you can say x and this is y. Okay, and you tied a you can see a rope. Okay, and then you uh, means, uh, then you rotate it, okay, along the x-axis, and it will means you just rotate it. So it will generate a solid. Means assume that means you are considering everything inside. Okay. Means you are obtaining a such type of solid. Now, suppose you know the equation of this curve. Okay, let's say y equals to f of x. Okay, and you are interested in the volume of the surface, means this generated solid. Okay, now let's so this see right now we are only we are considering this type point as origin, and let's take this is the point somewhere, say B. Okay, 0 to B. Okay, right. Now, and now what you can do is you can, as we have done in the case of Riemann integral, what we have done is first we have taken the partition. Okay, what we have partitioning the interval. Then we have means I just take, let's say h is equals to b minus a by n. So it's a is 0 here. So b is b by n. So you can increase n number of n and you will get a very small step size. Okay. So you just take a very small one part. Okay. And it means it will cut in a slice. It means you are cutting in a slice. Okay, so let me, my drawing is not that good, but you try to understand. So you are cutting a slice. Okay, so this is this. And you take this is length, you can say h here is let's say dx, or some instead of dx, what we have called is delta x I. Okay, or delta x, let's say this is uniform. Okay, let's take uniform. Okay, so this is delta x is equals to h. It's a very small. Now, and this is the interval, let's take between over the interval xi minus 1 to xi. Now you are interested in the volume of this part. This is very small part. And what you can observe is when you're talking about a very small part, okay, you can treat this as a right circular cylinder, because see, this will be treated as a straight line. And at any point, so in between you can tag a point. So like we have done in the Riemann approximation, you tag a point x star. Let's take x star is any point. So at any point, so what is the area of this cross section? Or you can not means like this is going to be okay, volume of this volume of right circular cylinder. If you know that pi r square h, if you recall. Okay, h is the width. Okay, r is the radius, and pi is there. Okay, so h is here is delta x. What is r? R is the radius. So at any point, you have, this is the last point, you have f of xi. For previous here point is the height is f of xi minus 1, and you tag a point. So that's going to be f of x star square times pi. So this will give you the volume of this slice. Now you take summation over I is equals to 1 to n. So over each interval, okay, so over each interval you are going to have a you are means every slice will have volume of this type over interval xi minus 1 to xi. Now you can increase and limit n tends to infinity. This n tends to infinity will give you, if everything is fine. So here we are assuming that everything is nice, means f is continuous. Okay. So if it is so, then it is this going to be, if in this case you have 0 to b, but in general you are going to be a to b I time f of x whole square dx. That will give you the volume of the solid of revolution. Okay. In this case, when you have this, okay. So this is going to be right now this is 0 to b here. Now this 0 can be shifted to anywhere, so that you can still talk about that. So it's fine, a to b. Okay, right. So this will give you the picture of how this will come. I mean this formula. Okay, okay, right. So now, so it's a explanation here. So just go with it once. Suppose the region is bounded above by the curve, okay, and below by the x-axis, where a less than equals to x less than. Okay. Now divide the interval AB into n equal parts with some intervals. Okay. Now approximate the slice of the solid by this one. For a point, this is a tag point. Okay, which we have talked about in in the case of Riemann approximation. Try to recall that. Then the volume of the solid of revolution is approximated by this formula. And then if I told you if everything is fine, that f is continuous, means pi time f of x whole square is a continuous function, then the limit of the above sum is required volume that is given. Okay, right. Now let's discuss the problem. Okay, once there's one problem, let's do it. Okay. So the reason is given here between the curve y equals to root x and x values are from 0 to 4 and the x-axis and the x-axis. So reason between the curve is revolved around the x-axis and which will generate the solid. So you have this explicit equation of f of x. Okay, find the volume of the solid of revolution. So that's here is integration 0 to 4 by the formula pi f of x whole square. At any point f of x is root x, so root x whole square dx. So that will give you the volume of the solid. Okay, now the question is, now it's see when the x-axis is revolved around x-axis. Now if it is the y-axis, means this this complete shape can be in the y-axis direction, means or y becomes the axis of revolution. Then what you will do, so you have the formula is when you have x equals to h of y, then okay, try to identify this x equals to h of y, and you have the limit of x y equals to c to y equals to d. Okay, same formula, this pi time h of y whole square here. When you have this. Okay. Now the formulas are simple. You are just to change x to y. That's it. And limits are also c to d here y. Okay. Now suppose it is not on the means x-axis is not. Okay. Suppose x equals to 1, or means like y equals to 1 is a axis of revolution, maybe shifting. Okay, right. So what we will do in that case, so let's take this example. So let's shift this. See, we know the equation of this curve is y equals to root x. Okay, this equation of curve is y equals to root x. So find the volume of the solid obtained by revolving the region bounded by y equals to root x and the lines y equals to 1, x equals to 4, about the line y equals to 1. So you are only revolving this, okay, about this. So you are going to obtain this. Now what you will do, you are going to apply the similar method, Riemann approximation and all. Okay, so you are see what you are required. You require the height. Okay, but f of x was denoting there is the height at any point. Now it was from this. Okay, now you have to look at from here. Okay, so now you know this is a y equals to 1 height, and this is y equals to f of x. Okay, so you can see, you know, this is f of x, and right, and this is y equals to 1. So this side at any point is going to given by root x minus 1. Okay, so that rest things are similar. Okay, so the volume of the solid will be given by pi time f of x here is now root x minus 1 whole square dx, and limits is x equals to 1 to x equals to 4. Okay, so now you can work with now anyone. So now y equals to x also you can take an axis of revolution, okay, and try to work it out. Okay, so this is the way to proceed for finding the volume of a solid of revolution. Okay, now let's move to find the volume of a portion of a surface. Okay, so okay, so for that let's try to understand this now. So you have, so let's talk about the volume of a portion of a surface. So of a surface z equals to f of xy over, means like let's talk about it on a rectangle first. Okay, over a simple geometry. Okay, over a rectangle. Over a rectangle, let's take R is a comma b cross c comma d, and I hope this rectangle R, I will just give you the draw of this. Okay, so that you can easily visualize this. So the first is correspond to x. So x equals to a to x equals to b. This is a, and this is y equals to c to y equals to d. Okay, so you are having this rectangle. This is the intersection of these 4 lines. Okay, that will give you the rectangle, okay, over which we are talking. Okay, now to obtain, we are trying to identify. So you have somewhere, see, whenever you're talking about volume, it's remain positive, and you're talking about above the xy plane. Okay, so let's have this is a some z equals to f of xy, and you have a one rectangle over which you are talking about. So let me draw a rectangle. This is there. Okay, let me draw a big one. Okay, so this is it's like this is x, this is y, this is z, and you have this is let's say this is a, this is b, this is c, this is d. Okay, now how to identify the volume of surface is as follows. So we are again going to apply now the Riemann's approach here. First, what you will do is you are going to partitioning both the direction. Okay, so when you are partitioning means you are going with half, this is let's say x naught and this is your xn, and let's say this is equals to y naught, and let's say this is equals to ym. Okay, so you are having partition, you are doing partitioning along the x direction, you are also partitioning along the y direction. Okay, and then you are making the lines. Okay, so let me draw. So you have means you will obtain a somewhere like okay, I think so you will get a rectangular grids. You are getting rectangular grids. Okay. Now let's say this is here. This I will denote this Rij. Okay, which is nothing but I have this is xi minus 1 to xi cross yj minus 1 to yj. Now I want to identify, so this is a very small element, rectangular element. Okay. Now I want to obtain a volume over it. Okay. So how? So I will draw a rectangular cube. Okay. So which will okay, so you may have okay, somewhere you should be with me. So let me choose another color here. So maybe black is fine. So in the Z direction, you are just okay. So how will you find the volume of this? Means you need to identify a height. So what you can see is you can get a tag point from this rectangle x star comma y star belongs to Rij. You will apply the same idea. So what will be the height over this point is f of x star comma y star. So volume is going to be f of x star comma y star time area of this rectangle Rij. That will give you the volume of this rectangle. Right. Now you take a sum over it. Double sum you have to take now. Double sum I over and j. That will give you the volume of the portion of the surface with approximation. Now, when you have n is tending to infinity and m is tending to infinity and f is continuous, okay, so that will lead to double integral, okay, at f of x comma y dA over r. Okay, so not that we are talking about f of x comma y greater than equals to 0. Okay, f of x comma y greater than 0. Like we have defined the area of under the curve. Okay, so similarly here for defining the volume of the surface, you need to be careful. F of xy should be above the xy plane. You have to draw in such a fashion. Okay, right. Now, is there any doubt in approximation? So area of Rij is what? What is area here? So you have this length you can denote by delta x, and this length you can means y direction you have delta y. So delta x into delta y is the, so you know, right, area of a rectangle is nothing but the length into width. Okay, so this is nothing but dA is nothing but dx dy. Okay, so this is will, so you can generate now as many as cube you can, means rectangular cube you can. Okay, and as small as possible you can take the rectangular grid. Okay, that will converge to this double integral that can be shown. Okay, so as m and n both tends to infinity. Now let's have the word, okay, what we have done so far. So the first statement is f of xy is greater than equals to 0 be defined on the rectangle. This is the rectangle which has, I have already given you one notation. Okay, right. So as told, consider a partition of R. So we will obtain rectangular grids, small, teeny rectangles. Okay. Then let's take area of Rij denotes the area of the rectangle, and let's choose. See this notation, you will be familiar after, maybe I don't know, you have done the norm or something or not. Okay, because uh, uh, when you are talking about the higher extension, okay, of a single variable, so non-negative value, okay, will be assigned with the norm. Okay, so let's not discuss about the norm here. So let's say this is a notation, okay, which will give you the maximum area. Okay, right. So now choose a sample point, which is a tag point as told. Okay, choose a tag point xij star yij. Of course, this I and j stands for the showing to dependence on the I and j. Okay, because they have been chosen with this rij. Okay, so then an approximation of the volume of the solid S is nothing but the following demands, no, as discussed. Okay, now if everything is fine, again I said, okay, that the limiting case when m and n tends to infinity and n tends to infinity, this limiting case will tend to the double integral. Okay, right. So this is what is happening here. You can also again see in the picture. Okay, so you have drawn a rectangular grids here. Rij is a very simple, very small rectangle, and if you generate all the cubes, you see you can approximate here. So this is the surface heights. Okay, you can simply, you can also by looking at the graph you can actually get an intuition, okay, that these heights are matching with the heights of f of xy at any point, and you are able to identify the volume of this. Okay, and this is what again wordings. Okay, if limit of Sm exists as norm p tends to 0, what is the meaning? What is the norm p tends to 0 means what? The area of the rectangle is tending to 0 because you are choosing very small dx, right? You are choosing this dx, delta x and delta y as small as possible. So that this if you have delta x into delta y, both are very small, means they are tending to 0. Okay, so whenever you have this, norm p is nothing but the maximum of that. So area is tending to 0. Then this limit is called the double integral, and is denoted by this. Okay, so whenever this exists, we say that f is integrable. As a definition we had, each continuous function defined on a closed bounded rectangle is integrable. So this you can observe as a result, okay, or some result, that if you have a continuous function and if you have a domain which is closed and bounded, what is the meaning of closed and bounded? Means it has boundary, okay, and that domain is of means like it has all the boundary points and it is a bounded domain. Okay, means it's how do you understand a domain is bounded? Means it is sitting in a, you can say, ball. Okay, it is sitting in a, here is two-fold ball, means maybe here 3-dimension you have three-fold ball, means like sphere. If you have a 4-dimension you have a four-fold ball, and so on. So I hope that that definition, you know, what is the meaning of ball? Means like disc. Okay, you can say disc. Sorry. Okay. So this rectangle can be covered in a disc in xy plane. Okay, right. If you have a rectangular cubes, okay, in xyz space, you can always cover it by a sphere. Okay, you can make as large as possibly. Okay, but not means as an infinite length sphere. Okay, infinite radius sphere. So it may be covered by a finite length sphere. Means like with the finite radius. Okay, right. So this is what the definition of rough definition of boundedness. Okay, right, of the domain. So when as long as the function is continuous, f of xy is continuous, you have the boundary is or I mean it's like a domain is a either a rectangular shape or is a triangle shape uh, or it's a disk. Okay, means you should not be worried. Okay, now I must say that you can extend this now definition to any direction now. You can include one more variable x comma y comma z. Okay. And means you can also find out that f of x comma y comma z is greater than 0 and triple integral meaning. Okay. By finding the finite length grids. Okay. Right. So again, as mentioned, see, it is not always possible to visualize the given equation, okay, or geometrically. Okay, means if you are extending one more direction is f of x comma y comma z. So then this rectangle means x comma y comma z is means in the t you have one another direction t. Okay, now this is the means you can say all this is a rectangle. What you can simply talk about the rectangular cubes now instead of rectangle. Now in each direction you will again partitioning. Okay, so in the partition here you are observing rectangles. Okay, when you are partitioning here you will observing rectangular cubes. Okay, small, very small cubes. Okay, and you know what is the volume of the cube is nothing but dx into dy into dz. Okay, and you can tag a point over which you can tag a surface and so on. You can talk about all this stuff. Okay, right. So you can extend this definition to any domain in this way. Okay, so let's have this example now. Okay, so find the volume V of the solid raised over the rectangle R. I hope now it is very clear what does it mean, and bounded by the plane z equals to 4 minus x minus 1. Okay, right. So you have so you have the rectangle is 0 comma 1 cross okay. So R equals to 0, 1 cross 0 comma 2. Okay. So in xy plane, so let me have in xy plane, so x is vary from 0 to 1 and y is vary from 0 to 2. So this is going to be the rectangle arc. So you have this is 1, this is 2. And you have the equation of surface is z equals to 4 minus x minus 1. Z equals to f of x1. Okay, and you again try to identify the volume. So it's obvious that you have this is going to be a plane, okay, which has the height at the most is 4. Okay, x comma y comma z. Okay, so you have somewhere this is let's say this here is y, so y is more, right? Y is equals to 0 to 2, and x is variable from 0 to 1. Okay, and equation of plane is z equals to 4 minus x minus y. So x equals to 0, y equals to 0 is a part of the domain. So you have 4, 4, 0, 0. Okay, means you have some downward plane. Okay, because it should be. Okay, so it's going to be some plane. Okay, something like that. Okay, so you can draw x equals to 1, x equals to 2, and you have this is so it's equal to 4 comma 0 0, and x at y equals to 2, you have an x equals to 0, so z equals to 2. Okay. So this is here you have 2 0 2, right? Now again you have x equals to 1, this is x equals to 1, and y equals to 0. So z equals to somewhere here is 2, here is somewhere 3. So you have 3x sorry, you are having x equals to 1, y equals to 0, and z equals to 3. And here is, I think, somewhere here is it's 0 to 2. I'm just trying to draw this. Okay, then you have some. Okay, so along this you have somewhere like this. Okay, some type of. Okay, here you can also point of intersection. Also, you can find out what will be the point possible. Now this is a plane, so you can now join. It will generate a solid. Okay, right. Now I'm interested in finding the volume of this solid. So as we have discussed, okay, so that's going to be double integral over R. F of xy is f of x comma y dA. So there are various ways to look into this problem. Okay, we are interested in finding this volume. Now here this is one way is means you can this is y is here is 0 to 2 and x is 0 to 1. Okay, now this is 1 comma 2. Okay, now one way is you can, whenever you are having this in between any line here, so you have this is, let's say, y. Okay, and if you draw a line parallel to this, because you are obtaining a rectangular grid, and then correspondingly you will intersect the surface. Okay, and so this equation of this cross section, so you are trying to get the cross sections. Okay, so x is fixed, right? This is going to be a function of y. Function of y. Okay, and y is running from 0 to 2. You can integrate over it. Okay, so what is a of y is nothing but, so you have the height here, so this is going to be what is A of y is equals to this area of this cross section, integration x equals to 0 to 1, because x is like from 0 to 1, and this is the equation is nothing but 4 minus x minus y dx. So this ay, and then this you can integrate along the y. Okay, so what it will give you, so we are trying to look at in some direction. So you have this is integration of a of y. This is going to be volume, then it's equal to integration of a of y dy, where y is running from 0 to 2. Okay, what is ay is equals to integration x equals to 0 to x equals to 1, 4 minus x minus y dx. Now someone can say that y in this y you can also have in the x direction. So similar concept also you can have, this is you can have also v equals to integration x equals to 0 to 1, some h of x dx. What is h of x is the cross section is equals to integration 4 minus x minus y. Again the equation will be the same over dy. Y limit is y equals to 0 to 2. Both will lead to the same answer. Okay, not only that, also you have the third way here, volume is equals to double integral over r f of x comma y dA. Now the question is what you do first with respect to x or first then with respect to y. So above discussion is telling you that you can move ahead in any direction, is that you can say that value will never be changed. Okay, so x equals to 0 to 1 and y equals to 0 to 2, 4 minus x minus y, and y is first limit, so you have dy, then dx. You have to write in this order. First limit is of limit y, you have to integrate with respect to y, and then with respect to x. And this both will be the same, integration 0 to 2, 0 to 1, 4 minus x minus y dx dy. Now you will ask that how this this change of order of integration will not affect. That is supported by Fubini's theorem. Okay, so if we have a function which is continuous, okay, over a rectangular region R, then order doesn't matter. Means R is a constant limit. Okay, so that's, so this value you can actually identify. Okay, so this the final value, so you can so volume equals to integration 0 to 1, 0 to 2, just going to finish this 4 minus x minus y dy dx. So that's equals to integration 0 to 1, 4 minus x times y minus y square by 2, 0 to 2 dx. That's going to be integration 0 to 1. So you have 2 times 4 minus x minus 4 by 2, that is 2 dx. Okay, so 8 minus 2 is 6. Okay, so that's going to be integration 0 to 1. 8 minus 2, 6 minus 2x dx. Now this is equals to 6x minus x square, 0 to 1, and upper limit minus lower limit will give you 5. So you can verify that previous results are will also give you this value 5. Okay, now as mentioned, the Fubini's theorem gives you guarantee the following: if f is continuous throughout the rectangular region R, then you can actually integrate with respect to any order. You're free to choose any order. Okay, but here the limits are here. You can see that C to D, A to B, C to D, A to B, C to D. Both are means all are constants here. Keeping that. But you may not be fortunate each and every time that you will always have a rectangular region. Okay, you may have a triangular region. Okay, so where one of the limit is variable limit. Okay, so in that case, what you will do, or in other words, if you have a non-rectangular region, what you will do? Okay, so then what you have a Fibonacci second form also. Okay, that will give you that result. Okay, so let's see if I have any. Yeah. So one problem is here, so that you can actually work out. Okay, so you have to evaluate double integral r y times sine of x into y dA, where r equals to this rectangle. So Fibonacci theorem will tell you that this double integral over r, this is y times sine of x into y dA, can be evaluated with any orders integration 1 to 2, integration 0 to pi, y times sine of x into y. Okay, and y is this is a dy and then dx. Now here you can choose any way. So I prefer to choose first with respect to x, then with respect to y, because if I first choose with respect to y, then you have y into sine of x into y. So both are functions of y. Okay, so you have to use the product rule. Okay, and in case of sine function, it is quite not favorable because sine is definite derivative is cos, cos derivative is sine. Of course, y will help you, but why to take risk here? So I can also look at this problem in this way: double integral over y times sine of x into y dx dy. X limit is 0, 1 to 2. Y limit is 0 to pi. Okay, now how will it help you is integration 0 to pi. So y is independent of x here, so y is out. Now sine integration, minus cos x into y, divide by coefficient of x, that is y, 1 to 2 dy. Now x equals to 1, x equals to 2. Now this y will get rid of, you are going to get rid of this, and what you are going to have is integration 0 to pi. Now minus sign is there. Okay, so cos minus cos 2y plus cos y. So cos y minus cos 2y dy, and now you can integrate. So cos integration is sine, right? But sine 0 is 0 and sine pi is also 0. In totality, you can verify that will give you 0 value. Okay, not that this 0 cannot be volume. Okay, because volume is always a strictly positive number. Okay, so if you look at the graphical link here, so I just have collected the graph here from the MATLAB. Okay, that it's showing that it has some, whenever you are talking about over the rectangle, it has negative part of the z because it's not completely lies above the xy plane. So here you will, whatever you are, it is getting in, it is getting drained here, you can see in the other. Okay, it is getting cancelled out. Okay, so you are not getting the volume. So for getting the volume, if you are interested specifically into the volume, you have to be careful where it is getting starting negative values. Okay, you have to break that, and the rest of the things you are going to measure with the magnitude. So like we have done for area. Okay, when curve lies below the x-axis. Sorry, below the x-axis. Okay, so you have to divide into two parts. So it's you can say over R1 and over R2. Two regions. So rectangular region, it can be a union of R1 and R2. Okay, right. So let's talk about how to work out with the non-rectangular region. So it says some very rough shape of any non-rectangular region. Okay, so what you can do is and still take an approach of it. Okay, approach similar approach here. Again, you will partition. You will draw vertical lines and horizontal lines. Okay, that will give you means as close as possible. So that will give you a small rectangle. So you will apply the same idea. Okay, as discussed previously. Okay, you are going to have the volume again in the similar way. Okay, you are going to get the height at the some tag point again f of x star comma xij star comma yij star into area of, so that is going to be area of rj, and perform the summation, double summation I equals to 1 to you have I is equals to 1 to n and j equals to 1 to m. And if f is continuous throughout the domain, you can also show that limit n tends to infinity and m tends to infinity, or in other words, you have this area is tending to 0. Okay, or maximum area, you can say maximum area. Right now, you can also work out with, if you are working with uniform mesh, okay, you can, because every area value is same. If you're not working with uniform mesh, means non-uniform mesh, means somewhere they are close, means these horizontal lines are close, somewhere they are far. Okay, so in that way you will get different areas of rectangles, different rectangles. Okay, so it's, so again, so this will take in the picture here. Okay, norm p is equals to maximum area of rectangle. You take out the rectangle and you take the maximum over areas. Okay, so if that tends to 0, means this n tends to infinity and m tends to infinity. Okay, that will give you that double integral over the rectangle or the non-rectangular. So let's take simple shapes of the non-rectangular regions. Okay, so let's have, there are two possibilities. Means there are two. Okay, not only two, but there are these two possibilities are there. Okay, I'm not saying only two. Okay, so you have one of this x. This is bounded by x equals to a. The first graph you can see x equals to b, and the curve y equals to g1 of x to y equals to g2 of x. So you have the limits is like a less than equals to x less than equals to b. This is the reason. And y is g1 of x less than equals to y less than equals to g2 of x. Like you had in the case of, means like when you are trying to identify area under the curve bounded by the two curves. Okay, so bounded by this region means you are going to, if you want to identify the area of this region, what you will do, area under the curve y equals to g2 minus area under the curve y equals to g1. Okay, so here is the difference. So you have this r is given by this, all the possible pairs such that this happens. Okay, so this is the first R1. On the other hand, you can also view it in the different way. Means like it's bounded by y equals to c to y equals to d and x equals to h1 of y to x equals to h2 of y. Okay, so you have this is R2 is c less than equals to y less than equals to d and h1 of y less than equals to less than equals to x less than equals to h2o. Now we have just now discussed, we are partitioning into rectangular grids. See, in between is everything is fine, but what about these corners, boundaries? Okay, so see, whenever you are having the limiting case, if everything is fine, these errors can be approached to zero. Okay, will approach to zero. Okay, because you are going to only do these are looks like when you are making the fine rectangular grids, they will be looks. So if you take any small part of this boundary, okay, any very small part, that will be looks like a, that will be a straight line. Okay, that will be say how you are parameterizing, right, how you are parameterizing the circle parametric, I mean that circumference. Okay, means you are going each. Okay, so here is it's if you take very teeny part of this, it's going to be loose. If you take a zoom it is a nothing but a line element. Okay, so as m and n tends to infinity, this error will be reduced and no problem. I'm passing the rectangular grids here. Okay, that error will be reduced. Okay, right. So now Fubini's theorem, just directly coming to the Fubini's theorem, that what this double integral over R. Okay, so double integral over R f of x y dA when you have this type of rectangle or when you have this type of rectangle. So Fubini's second form tells you that how to evaluate that. Okay, so second form tells you, so first thing is f is continuous. Just very, you can see this is a necessary thing right now. Okay, but not every time. Okay, so let f be a continuous real valued function on a region R. So that's a first reason. If R is given by this curve, this definition, okay, of course, this y is bounded by the continuous curve. Okay, we also want here nice functions. Okay, right. So then you are forced to go first with respect to y and then with respect to x. Okay, because when you are integrating two times with respect to both the variables, you are going to get a number if you want to understand by roughly. Okay, so when you are integrating with respect to both the variable, what you are expecting a number over a region. So as like you have expected in the rectangle. Sorry, as you have expected in the case of single variable. Similar here. Okay, so here you are supposed to first integrate with respect to y, then with respect to x, because y has a variable limit. Okay, now if instead of that, if x has a variable limit, you are forced to first you have to integrate with respect to x, then with respect to y. Okay, again this the x must be bounded by the continuous curves. Okay, right. So now with this, okay, so let's do one example. Okay, so now we are interested in finding the volume of the following prism whose base is the triangle in the xy plane bounded by the following lines. Okay, so you have, so in the xy plane, the base is, okay, line y equals to 0 is nothing but the x-axis, x equals to 1 is, this is x equals to 1, and y equals to x is the point. Okay, so this is the reason over which it is defined. Okay, now, and whose top lies in the plane z equals to 3 minus x minus y. I'm not going into the details. Zeros, you have 3 points. So you have, this is 0, 0. Here you have 1, comma 0. And here you will have 1, comma 1. So corresponding to each point, you will get a point on the plane and you can draw. So 1 point is for 1, 1, 0. You will have 1, 1, 1. You can also verify these 3 points and you can join them, okay, above the xy plane, and then you make it as solid, okay, which will come out as a prism. Okay, now note that here you have two ways to look into. So this is a y equals to x, because Now it's not a rectangular region. It's a, you can say, half of the rectangle, right? Double in means, right? If you make it join this as well, so it's a rectangle. Rectangle, in fact, here. It's not a rectangle. Now there are two. I have two ways to identify this region. This is R. One reason is, okay, either you move in this direction. So x equals to 0 to x equals to 1. So 0 less than equals to x less than equals to 1. And what is y? Is y equals to 0 to y equals to x. 0 less than equals to y less than equals to. Okay. Now another way is, I have, this is R1, both reason will be the same. I have another way is R2. Now x limit is, see, x equals to y to x equals to 1. So y less than equals to x less than equals to 1, and y limit is 0 to 1. 0 less than equals to y less than. Both reasons are same. Do you have any doubt in it? If you have any doubt, you ask me right away. Both will define the same reason. What? Because it is very important to get the right limits values. Okay. Everything else is very simple. Okay. So at the first stage itself, you must able to get the correct limit values. So if you have any doubt in R1 and R2, whether how they are equal or something, or they are representing the same reason what we are talking about, you do let me know right away. Okay, so if you don't have any question, okay. So now volume of the region, now you can anywhere, means you can either integrate with respect to R1 f of x comma y dA, or you can integrate over R2 f of x comma y d. Both ways will give you the same answer. Okay, so I'm just going with the R1. So double integral over R1, and what was f of xy is 3 minus x minus y dA. Now what is R1 is, I'm just writing here, R1 equals to x comma y such that 0 less than equals to x less than equals to 1, 0 less than equals to y less than equals to x. Okay, so this is equals to, as told, Fugle's theorem tells you, you are, because you are assuming here y as a variable limit, so you have seen the right hand limit or left hand limit. So left hand limit is constant, but right hand limit is variable. So you are supposed to integrate first with respect to y and then with respect to x. So y equals to 0 to x and x is 0 to 1. Now you can simplify it. This is integration 0 to 1. Now 3 minus x y minus y square by 2, 0 to x dx. Now that equals to integration 0 to 1. Now upper limit, lower limit will not contribute anything. So y equals to x. So 3 minus x times x minus x square by 2 dx. So that's going to be integration 0 to 1. 3x minus x square by 2. So minus 3x square by 2 dx. So that's going to be 3 times x square by 2 minus x cube by 2. You have 0 to 1. So that's going to be, lower limit will not contribute anything. So you have 3 by 2 minus 1 by 2. That is Okay, so you can verify that double integral over R2. Okay, you verify, I'm just giving you as an exercise. Okay, verify that double integral over R2 f of x comma y dA will also be equals to 1. Okay, right. So I think we can stop here now. Okay. So if you have any question. Okay then, thank you.
Thank you, sir.
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 Thank you, sir.